Hello everyone, I am Robin, third year computer science PhD student at the University of Houston. Now I will present our paper Configuring Test Generators Using Bug Reports, a case study of GCC compiler and Csmith. The correctness of compilers is instrumental in the safety and reliability of software system. Bugs in compiler are difficult to identify and debug. Random test generators are commonly used in testing compilers. However, guiding these test generators to produce effective test programs are challenging. In this paper, we propose kconfig that uses the code snippet in the bug reports to guide the test generation. We evaluated this approach on Csmith test generator and 8 version of GCC. Our approach provides higher coverage and triggers more miscompilation failure than state-of-the-art test generation techniques for GCC. Various approaches of test generation have been introduced to improve the quality of C compilers and find compiler bugs. For example, Csmith, a popular randomized test case generation tool, given a set of C language features, Csmith can generate random C programs that contain those features. It uses the randomized differential technique to find bugs in compiler like GCC and LLVM. Csmith supports configurable C language feature in the form of inclusion and exclusion. However, it is challenging to know which configuration is effective to control the features of the generated programs. An approach is swarm testing that configures Csmith such that test programs contain a random subset of the language feature. In swarm testing, the probability of choosing a feature in a test program is a fair coin toss. The recent state-of-the-art approach HiCOND utilizes historical data such as test program generated by the Csmith default configuration. It first infers the range for each option in the test configuration where bug-revealing test programs are more likely to be generated based on historical data. Then it identifies a set of test configuration that can lead to diverse test program through a search method such as particle swarm optimization. Finally, based on the set of test configuration, HiCOND generates test program through Csmith which are likely to be bug revealing and diverse. While our kconfig approach and the state-of-the-art HiCOND both use an initial test suite to infer effective configuration for Csmith, but they differ in two main ways. We use real bugs from bug reports, but they use Csmith generated ONs. HiCOND requires the configuration of the Csmith in the generation of each test program. In other words, all initial program must be generated by Csmith. Therefore, the test programs that are not created by Csmith, like the ONs available in the bug reports, cannot be used by HiCOND. Secondly, our approach can work with few failing tests, but they need a significant amount of passing and failing tests for such method. The particle swarm optimization technique used in HiCOND requires a large initial test suite of failing and passing test programs generated by Csmith. Unfortunately, as GCC matures, it becomes harder for Csmith to trigger failures in updated version of GCC, which negatively impacts HiCOND applicability on newer and more stable version of GCC. So our target is, can we use insight from bug reports to guide Csmith? This figure shows the workflow of test generation of our kconfig approach. Our approach contains the following main steps. We extract configurable test features from the code snippet of the bug reports. We then use Xmeans to cluster the test feature into similar groups. Then we use the centroid of the cluster as configuration of Csmith to generate test inputs for GCC. At step 1 of extracting configurable test feature, we collect code snippets that have been reported in the GCC bug reports. Then we use clung AST to extract the abstract syntax tree from this program. We count the number of occurrence of features in each test program to create a feature vector. We extract 32 configurable features of Csmith. Therefore, the vector size of a test program is 32. Feature vectors are then normalized to the range of 0 to 1 using min-max normalization. At step 2 of clustering test programs, we use X-means clustering algorithm that estimates the optimal number of clusters in the underlying distribution of data. Each cluster is represented by a centroid that uses that has a minimum distance to the data points of a cluster. Since the normalized feature vector contains the value in the range of 0 to 1, the value in the centroid would be in the range of 0 to 1 as well. The corresponding value of a feature in a centroid represents the probability of including the feature in a generated test program. Note that it is in the context with the swarm testing that uses the simplest form of fair coin toss probability for the inclusion of a feature. At step 3 of generating test program, so we use centroid in X-means clustering to suggest configuration for Csmith to generate test programs. To generate configuration, we use corresponding value of a feature in the cluster as the probability of including the feature in the test program. We test GCC with our generated test programs and continue testing until the total budget is. For each experiment in this study, we generate 10,000 test programs and take average by running the experiment 3 times to account the random effect. In experiment setting, we use Csmith, an open source automatic test generation tool for C compilers. So we select 32 configurable features from Csmith in the form of inclusion and exclusion from the command line options. We use the GCC regression test suite that contains around 6,000 parsable C code snippets. Those have been collected from the confirmed bug reports in GCC Bugzilla and test suite. And we use 8 versions of GCC under test, including the trunk version. This figure represents the characteristics of the bug reports. Here x-axis is feature list and y-axis is the number of test programs. Each bar shows the number of test programs in test suite for its features. It shows that the distribution of test features in failing test programs is not uniform. Features such as comma operator, global variable, and pointers occurred more frequently than features such as plus operator, shape math, or init. We observed that all 32 configurable test features of Csmith appear at least in 6 failing test programs in the regression test suite. We evaluate kconfig with 2 configuration generation strategy, round robin and weighted. In the round robin kconfig strategy, centroid of the cluster are used in a round robin fashion to generate test programs. In round robin kconfig, each cluster will have same test program generated. In the weighted kconfig strategy, the number of test programs generated by each centroid is proportional to the size of the cluster that the centroid represents. In weighted kconfig, larger cluster will have more test programs generated. We compare the effectiveness of configuration proposed by our kconfig with the effectiveness of configuration generated by the following 3 comparable techniques. Default. In this technique, we use the default configuration of Csmith, wherein all C language features are enabled by default. Then swarm. In the swarm configuration, the Csmith features are enabled by a fair coin toss for the inclusion of a feature. And HiCOND. The state of the HiCOND configuration are created by particle swarm optimization approach that attempts to optimize the effectiveness of Csmith by systematically exploring the bug finding capability of configuration in Csmith. We use differential testing to evaluate the behavior of the compilers on the test programs. We compile a program with different level of optimization and compare the output of the executed program. Due to the large scale experiment and time, we only use lowest level of optimization and the highest level of optimization in this experiment. We expect 3 types of compiler failures in the compilation of a program. On its crash, when compiler terminates the compilation with a crash report on the screen. Miscompilation, when the executor generated by the compiler produces different results on different optimization. And timeout, when compiler gets into non-termination on the compilation of a test program. In this experiment, we consider 10 seconds as the timeout threshold. Here is our results. Effectiveness of cluster waiting strategies. In this table, C0 means crashes found only on optimization level 0, C3 means caches found only on optimization level 3, and C03 means caches found on both optimization level 0 and level 3, and MC means the miscompilation failures. We evaluated two cluster weighting strategies, kconfig round robin that ignore the size of clusters, and kconfig weighted which generate test program proportional to the size of cluster. The result shows that in all 8 GCC versions, kconfig could trigger twice as more miscompilation than kconfig weighted. Although in the latest version of GCC both could not trigger any crashes, but in GCC 4.30 and GCC 4.8.2, kconfig round robin could trigger thrice as more crashes than the kconfig weighted in all optimization level. A potential reason can be that larger clusters represent prominent combinations of features in the bug reports. It is likely that developer already noticed and addressed them. Therefore, generating test programs from larger cluster may find comparatively less failures. For this reason, in the next all experiments, we continue only with the kconfig round robin experiment for our kconfig approach. The next one is coverage across generated test suite. This table shows the number of covered statements, branches and functions of GCC on high optimization level 3. At the time of writing, we did not extract the coverage information for most recent version of GCC like 8.1.0, 9.1.0 and trunk due to the difficulties of recent changes in the file structure in GCC project. So in this section, we only consider this 5 GCC version, and the coverage shows that in the major GCC versions among the generated test suite, the kconfig generated test programs have higher branches, statements and functions coverage than the generated test programs by other approach for all the 5 GCC versions that we experimented in this section. The comparison of kconfig with default and so on. Those could only found caches in GCC 4.3.0 and GCC 4.8.2. In total, in GCC 4.3.0, the default could found around 1700 caches, followed by 755 by kconfig and 666 by SOAN. However, a default did not find any crashes in GCC 4.8.2, where kconfig and SOAN both could find more than 100 caches in total. For MC, in all MC means miscompilation. For miscompilation, in all cases, kconfig round robin triggered the highest number of miscompilation compared to default and SOAN in all versions of GCC. And the kconfig could find on average up to 96 miscompilations, and SOAN could find up to 70 miscompilations, but the default only find 16 miscompilation in GCC 4.3.0, but it didn't find any miscompilation in other version of GCC. So in all cases, our proposed kconfig approach could find the highest number of miscompilation in all GCC versions. The comparison of kconfig with HiCOND. In GCC 4.3.0, HiCOND find the highest number of crashes on only optimization level 3, while SOAN followed by kconfig can find the highest number of crashes on optimization level 0 and on both optimization. However, HiCOND do not find any crashes or miscompilation in GCC 4.8.2. In GCC 4.3.0 and 4.8.2, kconfig round robin finds the highest number of miscompilation, then HiCOND and others. For timeout, the kconfig detects the highest number of timeout in optimization level 0 and in optimization level 3, and in both optimization, swarm followed by kconfig find the highest number of timeout, then the HiCOND. So in this section we only consider the GCC 4.3.0 and GCC 4.8.2 to compare HiCOND and kconfig, because HiCOND rely on a set of bugs generated by the default Csmith to search for the optimal configuration. As default does not trigger any crashes or miscombination on GCC 4.8.2, we therefore could not compute new configuration beyond GCC 4.8.2. Therefore, we only compare the kconfig and HiCOND in this two version of GCC. To identify the number of distinct bugs, we used correcting commits heuristic. It uses the commit where a test program switches from failing to passing as the proxy for the minimum number of distinct bugs. Due to the submission time deadline, we only compute the distinct bug for swarm and kconfig round robin in GCC 4.8.2. For the crash and miscompilation of failing test programs in GCC 4.8.2, the number of distinct bugs detected by the techniques are 3 only by kconfig round robin, 3 only by swarm, and 4 by both kconfig round robin and swarm. And we'd like to thank the authors of HiCOND to help us to compute the number of distinct bugs. So conclusion, this paper proposes kconfig, a test configuration generation approach that uses the code snippet in the bug reports to guide the test generation of Csmith. Given a seed test suite and configurable test generator, kconfig computes configuration for the test generator. We extensively evaluate kconfig with GCC regression test suite and Csmith on 8 different versions of GCC, including the trunk version. The results suggest that the usefulness of analyzing bug reports in the generation of the new test programs can help us to find the more interesting test programs. And the result shows that in all versions of GCC we experiment, our kconfig approach could find more miscompilation than the other approach and cover more statement, branch, and function than the other test generation approach that guide the Csmith. And our data and script are publicly available at the following GitHub link. Thank you.